This video is about analysis of covariance. Our objectives are to learn why we use it, how to use it, the assumptions that go along with it, the effect on sample size, and how to create confidence limits using the information from the source table. In this video, we're going to talk about analysis of covariance. Our objectives are to learn why we use it, how to use it, some assumptions we have to make, the effect on sample size, and how to create confidence limits from the source table. We're going to use the Chow Ortho-K database. And we're first going to look at our data for the different lens types. We had spherical and aspherical. We also are going to look at just basically the axial length at 5 years. So let's first create a box plot so we can see what we're dealing with. And define AL5 lens type. Okay. And here we see got two pretty overlapping box plots. Are they significant or not? That's a question we could ask. Is there a difference? So let's go up to Analyze, Compare Means, Independent Sample t-test. And we have our outcome variable AL5 and our lens type, where we defined 0 and 1 are the two. Type 0 is spherical and 1 is aspheric. So let's see what we get. Well, here are our group statistics. The means 25.5 versus 24.9. This is growth at our axial length at 5 years for the two. So aspheric is shorter. If equal variances are assumed, which seems to be a pretty good assumption since the Levene's test for equality of variance is 0.889. If they weren't equal, we'd use this lower row of numbers here, but it looks pretty good. So the t is 6, pretty high. That means we're 6 standard errors away from the null hypothesis of 0. The degrees of freedom are 376. That's because if you add these two up and subtract 2, you get 376. It occurs to me that I did not split for I. We'll do that. Maybe we won't do that. So, grapple. Shoot. We're going to use the Chow data set, the Ortho-K data set. Remember, there are two lens types that he used over 2 different periods of time, the spherical and the aspherical. And he used the spherical design for a while, then switched over to aspherical. We have done a propensity match here. It's already been done. So we're basically simulating a randomized trial by balancing on all of these baseline covariates. So we're going to look, our main question is there a difference at 5 years follow-up based on the type of lens that you used? So we're going to do AL5. But before that, we need to look at our data. And we're going to treat the data as independent values. So if we're going to do that, we need to split our file by I, because there are 2 I's and they're kind of not independent. So we're going to just see if we get the same results from both the left and the right eye. So let's do first look at the data by doing a box plot. And we're going to look at axial length 5 with the various lens types. Okay. And we see there's 95 left eyes and 94 right eyes in this matched data set. So eyes were matched separately from left, or were matched separately in the propensity analysis. All right, well, we're going to focus on the left eye, and the aspheric apparently looks like it's shorter, but is that difference significant? There's a lot of overlap there. So let's do a t-test. Analyze, compare means. We're going to do an independent samples t-test. And we're going to look at axial length at 5 years compared to lens type 0 and 1. Remember, 0 is spherical, 1 is aspherical. And let's see what we get. So we have our means, 25.5, 24.9. And so in both cases, aspheric was shorter. We look and we can, we tested for equal variance. They're equal. 0.751 is the p-value. The t is 4. That means it's 4.1 standard errors away from the null hypothesis with a p of less than 0.001. Degrees of freedom are 188. That's because if we sum 95 and 95, that's 190 minus 2 is 188. So it's n1 plus n2 minus 2. Also gives us the mean difference, standard error of the difference. This is what we're 4.1 standard errors away from the null hypothesis, and we get a 95% confidence interval of that difference. So, what about effect size? How big is that difference? So let's copy this, go into Excel, delete that, oops, delete that, and paste. And so let's look at the difference between the means. Now we're going to take aspheric minus spherical because spherical came first. It's kind of our control, if you will. And then we're going to do the average standard deviation. And I just noticed I highlighted the wrong thing for the means. So we're going to move these guys over. Whoops. Let's click on this. This guy here. This guy here. And we get an effect size of minus because aspheric was listed first and spherical is bigger. So minus 5.96. So it's a clinically relevant difference, but it's a modest one. It's near the minimum clinical difference that we would accept. But it's still a difference, and it's a reasonable difference. All right. Now, let's look at analysis of covariance. So what we want to do is we want to control for the differences at baseline when we look at lens type compared to 5-year follow-up. So let's do a scatter plot. And let's look at axial length at 5 years as a function of axial length at baseline, and set our markers by lens type. Now, let's look at this. What do we get? So, we notice that, well, let's double click on this and open up our chart editor. And then let's put in a line and a line of identity. So we just want y equal to x. So if there was no change over time, all the dots would be on this line because 24 here is equal to 24 there. So axial length at 5 years for almost everybody is a little bit higher. There were some people that kind of fell back, but why that is hard to say. It's probably measurement error or something. It's really hard to think that your axial length would shrink. So let's just let's see. So what do we want to do? Let's fit a line through each of the types of lens types. So want a linear line. I don't know why it's doing that. Okay. Now, what are our R-squareds? We look over here, we see that the aspheric lines are a little bit cleaner than the spherical lines. We get the equation inconveniently located in the center here, so let's get that out of there. I'm going to click on Attach Label to the line to get rid of that check mark, apply it, and the equations go away. Now we can see that for the aspheric group, the lines people are pretty much clustered. In this other group, we have a lot more variability. So we can, if you look carefully, you can see there are a lot of little blue circles down here. We can make those stand out a little bit better by clicking on spherical, hitting sphere, giving them some blue, applying it. And you can see there's lots of blue down here and lots of blue up here. And the red is pretty much tight to the line all the way through. Now, what we want to do with analysis of covariance is control for the baseline, because there's big baseline differences. And in our t-test, we had a spread. Our box plots were spread all along here. So if we look, we've got values going from like, well, this guy up here is about 29, and down here we're about 23. And so when we look at it, we're up here around 29 and down here about 23. So we have this big spread of data when we're comparing our t-tests. This makes for, in this example, there's a lot of noise here. And if we could get rid of that noise and just look at the separation after we've controlled, we've basically taken out what amounts to the slope of this line, and we've flattened it out. We had a picture like this that we've seen before that that looks like if we actually separate it into those guys that are around the blue dots, that are around the spherical dots, that are around the red, we can see that they're pretty close and they've taken out a lot of variability. If we look at this other group that is outliers, they're not close. They're outliers in the sense that they're very different from aspheric. We get these two nice parallel lines. In this case, we're looking at a likely problem we're going to create. The assumption of the analysis of variance is that when you do this, these lines are parallel. And the reason that's useful is because after you've taken out the variability due to baseline, the difference you're going to test is the difference between those lines. And you kind of want that difference to be the same across the entire area of the baseline. because then you can just compare simple means. Unfortunately, in our case, those lines do not look parallel. And so we have violated the analysis of covariance assumption. So the assumptions are just like in analysis of variance. There's normality, there's independence, there's equivariance. In this case, we're not seeing that so much in this case. So what do we do? What can we do? Well, there's not much we can do about equivariance. We're just going to have to live with that. But we can test to see if these lines are parallel. And the way we're going to do that is when we run our analysis of covariance, we're going to add an interaction term. An interaction term asks the question, are these lines parallel? Does the difference between lens type depend on where you are in the baseline axial length? We can see here that if you're starting out with a shorter axial length, there's a pretty big difference at follow-up. But if you have a longer baseline axial length, then there's not that much difference. So let's see how that plays out and if that's significant in our analysis of covariance. So to do analysis of covariance, we're going to go to the general linear model. And then within that, we're going to look at univariate. Multivariate is if you had a bunch of dependent variables. We only have one, axial length 5. Or if they were repeated. There's not repeated, although I could be considered repeated, or at least within. But we're not doing it that way. We're splitting the file and doing it separately. So we're going to do univariate. And here we go to axial length 5. As at 5 years is the follow-up, and the covariant is the baseline, axial length 0. And our test is lens type. Now, one of the things when you use this particular procedure, if we didn't go into this model option, it would give us a main effect of lens type and of the covariate. But we have seen from our graph that we need to consider the interaction. So the full factorial is not really full factorial in this case. We have to build our terms. And it's not full factorial. I mean, we are going to make it a full factorial, meaning we're going to consider all the factors. But this refers just to fixed factors, and this is a continuous variable covariate. So, and it doesn't give us the option of doing it all at once. So we're going to put in our main effects. And then we're going to put in our interaction term. Notice how I highlighted both of these. And then we add that. So we have a main effect of lens type, a main effect of axial length at baseline, and the interaction term. Now, one of the things we can do in options is to get our parameter estimates, which will give us a regression equation. This is basically exactly the same answer you would get if you did regression analysis, multiple regression. And our means, it only gives us lens type as a choice. The covariate is a continuous variable. You don't take a mean at every baseline point. So we don't get that. We could compare main effects, but there's only 2 groups, so you don't add anything. The F test is the same as the T test. And so what we get, we have our intercept term, just like we would in a regression. Lens type is very significant. Axial length at baseline is significant. But the lens type by interaction is significant. Now that makes our interpretation a little bit more difficult, because what this means is the effect of axial length at 5 years depends on where you started out at baseline. So we basically are going to ignore these expected marginal means, these 24 and 25, like in the t-test, which we just did. When we adjust for baseline, because we're concerned about baseline, we can't use these means because the means involve the interaction term. So what are we going to do? Well, we're going to basically transform our data, and we're going to create groups. Now, this takes us out of the realm of analysis of covariance and puts us into the realm of a full factor, not factor analysis, but a factorial kind of analysis. And we're going to recode our baseline data into a different variable. And so we're going to go down here, we're going to choose AL0, and we're going to call it CAL0 for categorizing it. So we're going to categorize axial length into 3 groups. Now, what are those 3 groups going to be? And unfortunately, I didn't figure that out yet. So let's go do that. Seems as I've done this before. So, yeah. So let's go to Analyze Descriptive Frequencies and go to AL0. And what we're going to do is we're going to split baseline into 3 equal categories. And so we're going to go into frequencies, and we're just going to go see where that would be. So the frequencies program gives us, for our left eye, we come down here and we see 33% of the people are less than 23.98. We're going to use 23.97. So over here, where we're recoding into a different variable, we're going to look at our old and new variables. We're going to look at a range from the lowest point to 23.97. And we're going to give that a value of 1. And then we're going to, okay, we'll continue that for a second. And we're going to come down and look at 66%. This is the cumulative percent. We did 33. Really, we want to find something less than 0.666666666. So that's going to be actually 66. So let's go to 24.98. So we go to our old and new values. Now our range is going to be the value 24.98. We're going to give that a number 3. It's 24.98 through the highest. And then everybody else is going to fall through the middle, so that's going to be all other values are equal to 2. So we're going to create, so we have these three categories, lowest through 23, 2498 through the highest, and those values between 2397, 2498 are the remaining ones, and they're going to have a 2. We get that from our descriptive analysis of the baseline. So we continue that, and we say OK, and we get these categories. So, for example, this first one, the category is 3. And if we look at baseline, 24.98 was really that big value. So that was, that's the value. We go. 26 is also up there, and so forth. And so we've got all our values categorized. Now, rather than using baseline AL0, we're going to do a factorial analysis with a category of AL0. So we're now out of the realm of analysis of variance, of analysis of covariance, and we are forced into doing a different kind of analysis, factorial analysis. And we have the factor of lens type by CALO. Now when we go to our model, we're just going to say we want a full factorial because we have two fixed variables now. We no longer have one continuous and one fixed. So we don't have to specify anything. We just say full factorial. And we're going to look at our means. Now an interesting thing is we have the means of lens type CALO0 and lens type by CALO0. So I want to do something that, well, we'll do it this way and then maybe show you what happens and then do it another way. Okay, so let's see what we get. Well, this time we lost so much information from our baseline that it kind of went out of significance, but we know there's an interaction. We're not going to go back. Maybe if we made 4 categories, this interaction would still be significant. It's significant in the right eye. So we're just going to keep considering it. Now remember, when we have an interaction, main effects are not really where the action is happening. So lens type, the main effect, these differences between these means, we don't really care that much about. You wouldn't do a graph of these and plot them out. The same way you wouldn't do category, the shorter, medium, and long axial length growth, or axial length at baseline. You want to look at lens type by baseline category. So we have our spherical equivalence here, and let's see. The problem is in graphing and figuring out effect size. It's just maybe a little more complicated doing it this way. Let's see what happens. So if we're going to have low, medium, and long. I should have said short. Short, medium, and long baseline axial length. And let's graph these guys like this. I'm not going to do this video again if this doesn't work out. Because to do the graph, in a minute I'll show you another way I usually do this. Okay, now we're going to go to select data. And then we're going to edit this first section which we're going to give it a name spherical. And then we're going to add, this wasn't a bad idea at all. Okay, we're going to add aspheric. And then we're going to highlight these three. And now we get our, we get our graph. And we can see that, well, let's, for a second here, let's come in here and let's go to design, add a chart element. Let's put in our legend. Put our legend at the bottom. So blue is spherical, orange is spheric, and you can see that the difference, just as we saw in that line, that scatter plot, the difference is big at the short end of baseline, medium, and not much difference here. So this is mirroring the the scatter plot that we had. All right, now one thing about analysis of covariance, and let's go back up to our original one. Well, we can't really use this one because we have the significant interaction effect. If our lines were parallel, we would use the standard error here, or the mean square error here, as our source of calculating confidence intervals and effect sizes. I'll go do it through the other one, but really, if we were to use this, we would look at our expected mean squares, which are of the, if the interaction term was not significant, we would use these lens types. And I want you to notice here that what these little superscripts are saying is these means are adjusted. They're not the same as the original means. So we have 25.55. Down here we have 25.53. They're not that far off, but they're different. And they're different because these are least square estimates. And by that we mean they've been adjusted for the original, for the values of baseline. So it's taken the parameter estimates, which is a regression equation. There's intercept, that's A, equals B1, which is lens type 0, times it'd just be lens type 0. And then this is a dummy variable. So if we were going to predict the value of the aspheric lens, we wouldn't add this. If we have a spherical lens, we add 10.09. And if we have axial length in there, then we multiply 1.04 times the baseline axial length, whether it's 24, 25, 26, whatever it is, you multiply that, add these guys up, and that's your predicted left eye for spherical lens, and with the 10. And if you were doing an aspheric, you'd do everything the same, except you'd use this one. And that's why it's important for those lines to be parallel, because the only difference in prediction between lens type spherical and aspherical is this constant. So it says it's 10 millimeters lens type. The spherical lens type is 10 millimeters longer. The problem is our interaction was significant, And so if you have lens type 0, then you subtract 0.388 when you are computing the lens type 0. So you take this 5.675 or 65, you add 10, and you subtract minus 0.38 times what the baseline axial length is. So it's a regression equation, and it gets complicated when you have the interaction term. But you have to do it when you don't meet that assumption. So we have shifted down to using it as a categorical to make managing this situation a little bit easier to see where the differences are. So we have our means at the different types, and that's what our graph is down here. Now, again, we would like to compute effect sizes and confidence intervals. And again, just like before, we use the mean square error term, or the mean square term, 0.523. So we copy this guy, and we come down here to our spreadsheet. And 5. Now, what we want to do then is take the square root of this. This is our root mean square error, and this value gives us our pooled standard deviation. And so to find effect size, we come up here to spherical. We say equals the aspheric short minus the spheric short divided by our pooled standard deviation. And we got that. And why did we get that? Why did we get that? Oh, because I put that over the text. There we go. So at the short end, this effect size is minus 1.16175. So let's copy that. Let's look at, actually we can just go like this. And we want to fix the standard deviation here, so we hit F4. F4 installs these dollar signs, and everything gets fixed. Now let's copy that. And you can see, just as the figure would suggest, big difference, less, and even less. And so the effect size is minus 1.61, 0.69, and 0.36. This last one's pretty small. It's less than our clinical relevance, but is it actually still significant? Well, we can answer that question by looking at the confidence intervals. So the confidence interval basically, let's see if our analysis, I'm going to probably fudge this a little bit for time's sake, but we'll look at our N is 95. We have 62, 61, 67 across both of these. We're just going to say our N is 31, half of this, because there's 2 lenses that go into this short period. So we're just going to divide that by 2, 31, and we're just going to make 31 the N. So to calculate a standard error, because remember our confidence interval is going to be the t-test times the standard error plus or minus the mean. So T inverse 0.16. Degrees of freedom are 31 minus 1 is 0. And so that's our t value. So we want to multiply t times the standard error to get our confidence interval. So that equals, let's get our confidence, or our standard error, which is the standard deviation divided by the square root of n, which we've said is 31. We're a little conservative here, but that's okay. And then we're going to say our 84th percent confidence interval is 2 times t. Now, if you were going to actually do this and you were writing your paper to be published, you'd calculate the n for each one of these groups and then use that to estimate your standard error for each of these bars. We're just going to use a generic one across the line. So there's our confidence interval. We're going to look at design, add a chart and an error bar options. Here it is. Custom, specify the value. It's that value right there. To go up, these are the positive error values, and this number does the negative ones, and so we have that. Turns out this one's going to be the same because our root mean square error is the same for both of these two conditions. It's a pool. It's an error across all of these groups. It can vary a little bit by sample size, but we did our best to make our samples equal by going in and splitting our sample into 3 equal groups. So we're calling them equal, even though they're not quite at that. So we want to add error bars, custom, and so it's this value and this value again. You don't, even though it's an interval, you only need to click on this is the difference between the mean and the top. And now we look, make this maybe a little bit bigger, and we can make our blue lines a little more transparent. Oh, fill, oops, more fill, solid, transparent. That way we can see if there's overlap. Solid, transparent. Okay. Oh my, making them conservative brought an overlap in here. So I probably should have gone through and done each of the ends, but you can see, hey, it's real different at the short end. Not so much, that's probably like a 0.08 or something. And this isn't even close. So interesting. I'm curious as to if I did something incorrectly here, because I thought they were all significant. But I think that looks pretty good. We're up here. We took